Thank you very much. Thanks for the introduction and having the chance to talk at this important conference here. My name is Fabian Fuerst. I'm from Opel Automotive GmbH and I'm from the Advanced Manufacturing Technologies department, and I focus on new technologies to support our paint shops and general assembly in all our locations in Europe. And this is my colleague from FZI.
Yeah, hello. My name is Georg Heppner. I'm from the FZI Research Center for Information Technology in Karlsruhe. We focus on technology transfer, so bringing the latest of the research into actual industry. So partnering up with Opel was actually a great opportunity to bring ROS into the real application.
We want to present our results from EUROC, that stands for European Robotics Challenges. That was a rather big European government-funded research project. Its goal was to get industry and research closer together, and there were three relevant challenges where we participated in the first one: reconfigurable interactive manufacturing cell, and there were also shop floor logistics and manipulation, and plant servicing and inspection. The setup of the project was that over 100 teams began in a qualification phase, and after each phase, an independent jury of mainly professors from important research institutes from all over Europe assessed those project progresses and decided who of the teams will receive funding for the next stages. And yeah, we made it quite far. So the project began in 2014 and ended this year in summer. As I said, over 100 teams from all over Europe. Coordinator was Bruno Siciliano, and the overall project budget was 8.3 million euros, where 7 million were granted to the challenges. Our team consisted of the FZI, who did software development, design, integration, and pretty much developed the overall application, and they did a very good job. We also had MRK Systeme on board. MRK is German, stands pretty much for Human Robot Collaboration, HRC, who provided the hardware, did the safety concept, and constructed the gripper. And we as Opel defined the use case, especially the requirements also regarding safety, and we set up, we try to keep everything in line to support our goals to get it closer to production environment. And after these 4 years of overall project, we were awarded with this great award. We were very honored. Yeah, we won. Do you have the rubber band? Yeah. So the use case, which I will describe now, or right now I will describe how we do it today in the plant. So we have this rubber ceilings which need to be mounted to the door, and it looks it's this component, and we have these pins here. I'm not sure if you can see that from everywhere. They are rather small, and they need to be mounted into dedicated holes in the door. So you can see that here on the pictures, or you cannot see it on the pictures, but you can see it here on the tiny pictures on the top where they need to be pushed in. And the process looks like that today. An operator stands on a platform a bit higher than the ground. He picks this rubber band from a rack, looks for the first pin. It's about 40 pins, roundabout. Depends very much on the vehicle, around about 40 pins. Looks for the pin to start with, because the distances between between the pins vary. So we have one pin for one location dedicated, and then he pushes in those pins. The operator today does about 20 pins. The first operator does about 20 pins, which are on the upper part of the door, and another operator stands in the next station a bit lowered, and he puts in the lower part of the rubber band, and two operators assemble two doors per minute, or two rubber bands per minute, but also do some other stuff. So they are not totally on only pushing that in. And as you can maybe imagine, that it's really tough if you push in 40 pins per minute for 8 hours a day. That is, let's say, straining for the thumb. It's not ergonomically critical. We don't have critical operations in the plants, of course, but let's say the operators prefer other stations to work in. Since we have many plants and this needs to be performed everywhere in all our plants, it makes sense to have the teaching process very simple, very fast. The polymer is flexible, and that's really a challenge to do that with a robot, to handle these flexible components. It's very force sensitive, but Georg will go more into detail into that. And we have a very open workspace with moving lines. You can see that on the picture. It's a picture from our lab, but it's very similar if you take a look at the conveyor. So we always have two doors in the conveyor, one front door and one rear door. Usually, in this case, we have two front doors, but as I mentioned, only in the lab, and they move continuously. And it's very tough to have that automated because we simply do not have the space to get in standard safety fences. Why we participated in this project was that we all know many research projects which are based on ROS, but it's very rare to see real applications in production. And we wanted to take the step to get as closely as possible to a real production environment, and especially considering the safety standards which Mr. Buhlmann just mentioned before, or answered the question if it's possible to have it ROS in a safe environment in the real production, and he said it's very challenging, and yes it is, but that's exactly what we did, and that's why we participated here. We decided to use to choose this application because it's very high sophisticated, very unconventional to use or to assemble such a rubber band. It's, as I mentioned, force sensitive. It's actually in a moving line. For now, we did it in a stop station, but that would be the next step. We have in general assembly very high equipment availabilities which we need. In body shops, it's a different situation. Here we calculate with, I think, 95% uptime in our lines. So we foresee 5% of the time for maintenance and breakdowns. In general assembly, since we do pretty much everything in manual processes, we calculate with 99% uptime. And if we want to get in an automated process in there, we also need to make sure that we can keep up with this 99% availability. Otherwise, we lose a few cars which we do not produce. And the overall project is scalable. It should be low cost, and it's not automatable until now. And with that, I want to hand over to Georg.
Thank you very much. Is this the clicker, actually? Yes. So I'm going to talk a little bit about what we did and what we implemented. So first of all, everything we did was based on ROS, and we used ROS for every step along the way. As we heard previously, we had multiple stages during UROC, and after each stage we had to fear that we were kicked out, but fortunately we made it all the way to the end, and we tried to factor this into our development process and try to use each stage for individual parts. So the first one on the left is the benchmarking phase, and in this we were given a task to assemble an inlay, and sound insulation inlay, into a car door dummy, and this was the same task for all of the participants, so we did have little choice in what sensor or robot to use, so we instead focused on making the application as flexible as possible to give us a good fighting stance for the later stages where we had to tackle a lot more difficult challenges. And then the second one is the freestyle stage, and in this stage we could actually set ourselves some goals which were then evaluated by the other partners, so don't take something that is too easy, and we've chosen to focus on easy teach-in and easy adaptation to new car door variants and to new paths that we want to execute. And then the third one here is the showcase, and this is actually a realization of the use case that we just heard about in a lab-like environment. So we were still able to cut some corners and basically show that it is viable to do this application overall. And then in the final stage, in the pilot experiment, we actually had to bring this into the application at the Opel plant and consider more things like safety, some standards, the Werkssicherheit and things like that. So all of that had to be considered. So for the first step, the benchmarking, as I mentioned, inserting of this car door inlay, and this was the given task, and also there were some variances. So we knew roughly where the doors were, we knew roughly where the inlays were, but they could all vary for about certain centimeters. So what we did was we worked heavily with learning or teaching of predefined sets of poses, trajectories, and certain steps along the way. So for example, you see in the top right, we used a PMD depth camera to localize the door by stitching point clouds, then doing a contour extraction and finding out where the door is. But then in the next stages, we would actually define all the work steps with this car door in relation to this previously found door. So we step by step built up our environment, our 3D scene, and then worked with all the steps afterwards built on this relative information. And also we used, of course, tools like smart state machines for increased reuse. So screwing in one screw would be reused again and not done differently for every screw. We later switched to FlexB, which is a little bit more flexible and easy to use. And we also started with force-based operation, and I will just show this in a video. So we didn't control the sensor setup, so we were very limited in what to use. And we used the PMD depth camera on the front, stitched together certain rounds of moving around in the rough area where we thought that the workpiece was, so it was given as a rough estimate position. Then use contour matching to extract the center position, and could work from there. So after finding out the positions here, and you see all these movements here are then relative to this. So this pickup position we taught manually in advance by learning the object center and then teaching where in relation to this object center we wanted to pick this up. And this is quite straightforward, but it worked really, really well. And then during the insertion, you can see that the wrist of the UR is moving slightly. We unfortunately hit it straight away, but if we didn't, we would have adjusted to that by using a force control approach, which we later extended into a much more sophisticated version. Also, we had to pick up some screws and insert them, and this was also done with a force-based control. So you can see that we move onto the holes to screw it in, and then backtrack a little bit to actually reduce the pressure before we then move in with a constant force to not get the screws stuck. And this proved to be working quite well. And we could adapt everything to our needs by just retouching certain paths, certain positions, and quickly adapt to changes. And then in the next stage, we focused on doing this teaching a little bit more sophisticated. And here you can see the cut-to-path solution that we developed, which is a web-based tool in which we load the CAD model as a 3D model and then simply draw onto it. And by this 2D drawing, we project this line onto the surface, follow the contour of the object, and can then transfer this into our ROS backend, which would then take this robot-independent trajectory, map this onto our actual robot, which can be a UR10, and you will see later on it's a KUKA KS16, so we are not really dependent on the actual type of robot that we use. And then we can execute it straight away. And you can also see now that we follow the orientation of the surface by keeping perpendicular at basically any state. In addition, we also use a force control at this point, so we try to keep a constant force onto the door to keep a slight pressure and draw onto this. And this is, of course, very useful to teach very complex paths, which would require a lot of time doing this manually and doing it very intuitively. So we later show that basically everyone can use this. We also looked at other methods. So in this case, we just gave the robot 2 points, a starting point and an end point, told it to do a movement straight away, and then it adapted its orientation along the way based on the force values we got from the force torque sensor. And this adapted a spline interpolation, which then learned the surface contour. But it takes quite a while. You see it sped up quite drastically. So the cut-to-path was the easier tool. And also we looked at adaptation. So in this case, we had a trajectory learned, but then during the execution, we could just go in and move the TCP around a little bit. You see I'm shaking because it's based on time and I need to be very precise, and I screwed up the first time, so that's why I'm shaking a little bit. But it worked really well, and this is especially useful to do small incremental updates directly on the workpiece without going back to the teaching itself. And you see on the reproduction step, on the second way through, we have adapted our spline interpolation in the back and then can execute this again with the new learned support points. Okay, so going back to the actual use case, Fabian has already told a lot about it and the difficulties, and I just want to go quickly over these 4 key challenges that we see. So first, we have various doors, we have various types of cars, and everything is a little bit different, so we needed to have a fast way to teach everything, right? Then second, we have a flexible polymer, and up until that point, we didn't see any solution that was able to handle flexible polymers or flexible handling in that scenario, because if you lose this sealing once, you have a problem. And then the third one is that actually inserting the pin is a really hard challenge, because this pin can have an arbitrary orientation. So we really need to feel it, and of course we had to keep safety in mind. So what we did was, for the first part, we had further adapted our cat-to-path tool, and we enhanced it by adding a hole detector. So the user just marks the individual holes, and you can see down in the bottom, there you see the individual TFs created for each of these holes. But this gives us the added benefit that we have a trajectory going from one hole to the next, sticking very close to the surface of the actual workpiece. And you will see in the video that this worked quite well. So with this, we were able to train a new door model in under 5 minutes, which is a significant speed up to 2 days. So even an untrained worker that has never before seen this tool was able to handle this in 7 minutes. With just a little introduction of, hey, you can use these buttons to do stuff. So then the second part is handling this flexible polymer. And we thought a lot about how to do this, and then we've chosen to do it exactly like the human would. So the human grasps the sealing, puts in the first pin, and then never lets go of this sealing. He just moves his hand along until he finds the next pin. And we tried to opt for the same approach. So we used a standard industrial gripper, the PG Plus 7T, which is compared to a complete custom solution, a really cheap option, and just opted to create special claws for that. And you can see that we did quite some iterations, mainly in rapid prototyping fashion, to get it right. And with that, we can clamp this gripper down, so we hold the sealing tight, but then release it a little bit and move along the sealing, gliding through it. And with this, we were able to safely work with this, safely operate with flexible polymers. A very neat trick. And ROS helped with this quite a lot deal because these iterations were really, really fast. Sometimes we would try out 10, 15 different designs on one day, basically, by just exchanging individual parts. But every time you have to adapt the software too. You have to tweak a little bit. You have to set some different stops. And having a flexible software really helps with that. And then I mentioned it in the beginning, we also looked at force control, or more to say compliant control, because in the end we developed a new controller scheme. We call it forward dynamic compliant control, because it is actually a force admittance and impedance control all in one, and we made this robot independent. So it's basically an add-on solution doing the force control all in ROS and then controlling the robot, so we could quickly exchange the robot doing this. It's of course not the high update cycles that you would get from doing it all inside the controller, but this was a really, really versatile option which gave us the ability to do something you see in the lower right, to actually orient ourselves in the best way possible to mitigate the forces that we encountered. And for example, if you take this ceiling and you insert it, at some points you were even touching the rear wall, because there's really not much way of inserting this, and you only had a certain millimeters of space. And with this, we enabled this force-based dexterous assembly, and of course this can be used for a lot of other applications, as we will see later on. And also mentioned in the beginning was the security system, or the safety system, and we thought a lot about this, and in the end opted for a hybrid approach. So we use traditional safety laser scanners to produce safety scanner fields. But in the outer safety zones, where the safety is not yet violated, we completely rely on ROS to stop. So we upgraded our drivers to be able to be paused. So when we walk in the outer areas, then the robot will be paused completely in ROS, and we can ramp down safely. We stop everything that we do. And then if we go into the inner field, the external PLC will simply check if we did everything right. And if we didn't, it will fire an emergency stop. But if we did, everything is fine, we can just go out and then continue on. And with this, we were able to do a safety system where we could work in close proximity. We could go into the process at any time, and we were able to implement this on the Opel site. And the factory safety guys said, okay, it's good to go. You can work here with people of the line. So all of this combined, I wanted to show you in a video highlighting how this would look. So this is the robot that we ended up using. We wanted to have another, but that got thrown down by DHL. So we used this one, and you can see we got on top there a little process monitor showing what is going on, which pins have been inserted. We have the robot control on the right. This is a movable base, just a little bit, made a little bit heavy, and then we have our teach-in system, the cut-to-path tool connected to a ROS control PC, then executing the actual assembly. And you can see I start here with the model loaded, and I use a touch screen, which is quite nice to use, to go around this model and then just highlight or indicate each of the holes where I want a pin to be set. And we mark the individual holes, then do a hole search algorithm to meet the exact center of that hole, and then extract that back to the ROS system. And this robot previously had none of the trajectories required to do the actual assembly. Some maintenance trajectories, like this move into grab position, were previously on the robot, but everything else was just created. So then the robot checks the environment with the laser scanners, and has multiple fields that are being monitored, and it indicates to me that I can go in and put in the ceiling, because we wanted to show some kind of cooperation between a human and a robot. And in this case, I'm asked by the robot, okay, now you can go in, everything is safe. I go out, tell him, okay, everything is fine, continue working. and the robot will continue. And you see, in a minute I will step in because I forgot something. I wanted to check if everything was still all right, and I will just go into the zone, and you see that the different zones will trigger. The robot stands completely still, and at this point, if the robot did any movement, it would trigger the emergency stop, but it doesn't, so it continues working after I've gone out. And this, I think, is a very viable approach to bring ROS industrial applications into the production, but still relying on some safety without compromising the process efficiency. So then you've seen the first pin was set quite fast, and it is hard to see, but we'll see in a close-up in a short while. We then open up the gripper, and we can move along the surface of this door very, very closely, because we actually have this surface-based trajectory out of our cut-to-path tool, which we used previously. And here you see a close-up of how this is looking, and you see that we do a search movement, because these pins can have an arbitrary orientation, and we don't actually know for sure that the pin is oriented the way that we think it is. And at the second point now, we deliberately put the hole a little bit to the left. So you see, if we touch down, we realize, okay, we are not perfectly centered in the hole. We do a search movement. We get in there, and then based on the force profile that we detect of this operation, we know that we are inside the hole, so we actually feel what is happening, and then a pneumatic cylinder you see on the top will push in the pin for the final operation. And this, of course, works all around the door with all the holes. And we were able to mount the complete ceiling with this in about 11 minutes, which is unfortunately not fast enough. But it was about 40 pins. If we wanted to mount it in 1 minute, we had quite a short time frame for each pin, and doing such a complicated insertion is really a hard challenge for that. Okay, so short recap of what we learned, or what ROS Industrial brought us for this project. And it was really, we could add a lot of benefit to it by using the ROS tools. Of course, we have visualization, we have drivers, we got all the nitbits that make ROS nice and easy to use, and that speeds up development significantly. But also, we can add robot-independent research, such as the force control or such as the teach-in UI, that we have now independent of the robot, independent of the application use case, to use in different scenarios as well. And this adds a real great value, I think. Then third, we did a lot of prototyping with this, because handling a flexible strip has never been done. So we needed to figure out how to do it in a nice way, and ROS really helped in speeding up that integration. And last but not least, we've shown a safety system, which is not, of course, the state-of-the-art best. You can get wonderful collaborative vision, which I would like to see, but as that is a little bit out still, we opted for the next best thing, and that was bringing a ROS application into the real plant with a safety system that works. Now I'll give back to Fabian, who tells a little bit about transferability of these things.
Thanks. Yeah, as mentioned, we managed to have to combine ROS with standard technologies for safety purposes. We did the risk assessment totally in-house, completely in-house, with our standard team for machine and plant safety, and they were very happy to certify our prototype here. And the open workspace is especially attractive for all general assembly environments, and also for our powertrain plants. The safety concept can also be transferred to machine unloading in press shops, for example, machine loading in body shops, where we still have many operators who work in these areas. In general, you can use it for handling of components and sub-assemblies, and we will also focus on screwing operations in powertrain and general assembly. Also, I wanted to show one application which we currently develop in a human-robot collaboration. It's the glass assembly for the front and rear window. It's a combination of a fully automated process and human-robot collaboration approach. So what you can see here on in the front on the right is the rack where the rear windows come in sequence. A robot picks them from the rack, puts it onto a centering table, so we know it very precisely where we have it in the gripper. We apply the primer, which currently is performed by our suppliers. We give it back to the centering and turntable, hand it over to a second robot who applies the adhesive bead, and which will finally hand it over to the mounting robot, who synchronizes with the line. It's a moving line. You can see that on the picture on the right. And here 2 operators can enter the area and assemble the window. And we saved, currently we have fully automated stations or fully manual stations, and that's a mixture in between, so it's quite in the middle between invest and running costs between both other concepts. So we can offer something here as well, and that's where a similar safety concept or the same safety concept can be considered. Force-sensitive operations, you can see that here. It's screwing operations. That's one of our main focuses, where we want to apply more robots in our production lines. On the right-hand side, you can see our first human-robot collaboration approach from a couple of years ago. It's a CR35 Fanuc, who performs the screwing operation, and also on the left-hand side you can see a concept developed by FZI. Coming to cut-to-path, it's easy, as you hopefully learned from Georg. We have about 130 meters of adhesive beads and in body shop and GA, and we think that we can lower the teaching time significantly. A guy from our paint shop said, who is responsible for applying all the sealers, he said he could most likely save about 40% of his working time. And on the video which you saw, here we applied an adhesive bead to the Zafira window. We made a survey within our plant. So we had many people from different areas, coming from directors, department leaders, group leaders, engineering, from engineering also down to the operators in the plants, and they all had the challenge to teach in the assembly of the rubber band here, of the sealer, and goal was to do it in about 15 minutes, and everyone was capable of doing that, and I think in average they took about 7 minutes, so but it's very fast, especially for people who have never ever programmed a robot before, and that's a very tough challenge. Coming to conclusion, we were capable of combining ROS with a production environment. Still had it in the lab, but we proved that it's possible. We did that with a combination with pragmatic safety equipment or standard safety equipment. We performed a real collaboration. Most applications from human-robot collaboration I've seen so far are not really collaborative, but more coexistent. So it's also possible. Flexibility and robustness are often very contrary requirements. We will focus definitely on an easier application to have it in the real production. It was, to be honest, it was too challenging to get in 40 pins in less than 60 seconds, and you only have 1 second or 2 seconds for each pin, and that's not doable today. Force sensitivity needs to be much faster to perform that many tasks in less than a minute, and parallelization is also not possible here. Next steps. We want to prove that the concept works also in the moving line, as in general assembly everything is moving. Makes it even tougher, especially for force-sensitive applications. We need to combine it with vision systems, and we have to do the first implementation in production and not only in production environments. And we hope that FZI will increase the cut-to-path maturity, so we can finally buy it and use it to teach our robots. And with that, I want to thank you for your attention, and we would be now open for questions.
Okay, thank you for your very interesting presentation. We have time for a few questions. Okay, well, one is over there.
You mentioned you used a state machine-based approach to model the software behavior, and you first used Smash and then then switched to another tool.
It's FlexB, flexible behavioral engines. It's basically the same thing, but a little bit different.
But with a graphical user interface, because from my point of view, it would be very good if you want to collaborate with people from the shop floor to show them what you're programming and to do it both. Yeah.
Mm-hmm. It has a user interface, and
Okay.
it's a little bit easier to use than SMAC. Or a little bit nicer to use. I would still not consider it to be a tool for the shop floor, but it definitely helps in doing modular approaches like this. But I agree with you totally if we had a nice and easy way. But the problem is you always have to balance out easy use on the shop floor versus the things you can do with it. And that's why we opted for hiding most of the complexity of the actual application and just giving the things that would change, which is the car door variant, the positions of the clips, to the users in a very user-friendly interface that is easily understandable. So I think always have to consider what is the right option for this.
Very impressive manipulation work. I'm just curious, what are the failure modes as you speed it up? Can you just turn up the velocity, or what do you need to do to get that 60 seconds? Do you need 2 arms or better physics modeling?
We thought about that a lot, and it's not that easy to do this. So the process of inserting the pins is actually quite complicated because we need to feel this orientation. We need to make sure that we are in. So I think one important step would, of course, be speeding up the force sensitivity of the robot, the control that we have there. And I mentioned we had this first phase where we showed that it is possible. There we had a time of 45 minutes for a complete door. We sped that up to 11 minutes by, for example, eliminating certain steps like doing the push-in with a pneumatic cylinder. But even considering that, you would have to keep in mind we roughly have a second per pin, and then we need to move on to the next pin. So I guess in order to reach a minute for this application, I think you would need to have a whole different approach. Maybe use multiple robots that fasten it on multiple sides. I think we cannot reach the 60 seconds with the current setup, but we are pretty close, and I think we've shown a lot of the technologies that you could use in something that maybe has a little bit more time or a little bit less pins. Also, an idea was to basically just put in every second pin and then have a human just go over and push in the remaining ones, which is a feasible thing to do, but still not reaching the 60 seconds. So.
Yeah. I would totally agree. I think the application was just simply too challenging, and we are currently not seeing that we will go with this application into production. But we will transfer the force sensitivity to other applications. I mean, take your vehicle apart tonight, and you will find so many force-sensitive applications which we need to perform in our plants, and we will go for other applications first. And I mean, it was a research project. Otherwise, we wouldn't have any legitimation to participate in RIC. So we knew that will not be capable for production before, and but we learned a lot, and we can transfer it to other applications. Also, our competitors use completely different methods to get in the rubber band, the sealer. They glue it. And yeah, so sometimes you need to think outside the box. I think we will also go there, I think, but I'm not from serious planning, so I cannot really tell. But I would, if they ask me, I would not recommend to go for full automation with pin insertion or flexible component.
Okay, so once more, let's thank our speakers.